So let's explore this third part of the central limit theorem, the part about standard error. So here we see the standard deviation of means is equal to the standard deviation of the population divided by the square root of sample size. So this means that if we for some reason knew the standard deviation of the population, right? Let's say it was like 5, right? Then we could just directly calculate the standard error if we also knew the sample size, right? Do you think we'll get the same numbers by doing the calculations versus if we looked at it, let's say, through simulations? Let's try it. So here I'm going to create a little table where we're going to look at a few different sample sizes. So sample size is notated with the letter N, right? And so we could look at a few different sample sizes like 2 and 5, 16, 20, 25. And then we could also just directly calculate the standard error based on the central limit theorem. And then what we could do is we could use our simulations to actually simulate the standard error. And we could compare and see, do you think the calculated standard error and the simulated standard error are going to be pretty close? I wonder, right? So notice that I don't know anything else about this population so far except the standard deviation is 5 in this population. And just from that information alone and the size of the samples, I'm going to be able to predict the standard error. That's kind of amazing, right? So I'm in Excel, and so I'm going to use the equal sign to ask Excel to calculate something for me. So I'm going to say, 5, that's sigma, divided by the square root. Excel also has functions like r, and square root is exactly the same function. And I'm going to say square root of 2, my sample size. And then when I hit enter, Excel is just going to calculate it for me. It's going to say, oh, it's going to be 3.5-ish, 3.54. Do you think I would get a standard error of 3.54 if I simulated this? So here we have our simulations, and we've set our parent population to be normal with a standard deviation of 5. Now, if I create a sampling distribution of means from n equals 2, will we get the same standard error that we got from calculating it with the central limit theorem? Let's see. So I'm going to directly calculate 10,000 different samples means. And let's look at how variable those means are. Okay, so here's the standard deviation. This is the average distance from the mean for all of these means. And that number is 3.52. Hey, 3.52 ain't bad, right? That's pretty close to what we got from just calculating it. Interesting. I wonder if the same thing will work for sample sizes of 5. Okay, so here's 5 divided by the square root of 5. We predict from the central limit theorem that this is going to be, the standard error will be 2.24. I wonder if it'll be pretty close when we simulate it. So let's clear that distribution of means for n equals 2, and I'm going to change this to n equals 5. I still want a sampling distribution of means, but now my sample size should be 5 data points. Okay, so let's do 10,000 samples. And so here we see that the standard deviation or standard error is 2.2, 2.23. Whoa, that's pretty close. 2.23. Right. So let's go ahead and make these predictions for sample sizes of 16, 20, and 25, and then let's fill in these numbers by simulating them too. And just to make this the same in this column and this column, I'm just going to delete the So it says this is the calculated standard deviation, and here's the simulated standard error. It's going to be 5 divided by the square root of 16 And this is going to be 5 divided by the square root of 20. And we think this will be 5 divided by the square root of 25. Notice that these standard errors are becoming smaller and smaller. So that means on average, the means are varying less and less and less, right? Will we see the same patterns when we simulate? So I'm going to change this to n equals 16 as well as n equals 20. And let's simulate 10,000 samples. Oh, I forgot to click mean here. So 10,000 samples. And what do we see? We see the standard deviation of n equals 16 is 1.24, and for n equals 20, it's 1.12. I'll also look at the standard deviation for the distribution of means when n equals 25. So that will be 1.01. So we'll just finish filling out our table right here, 1.01. So these were all the numbers that we got from our simulation, and these are all the numbers that we got from calculating it based on the Central Limit Theorem, the third part of the Central Limit Theorem. And what do you notice? They're all pretty close, right? So this is pretty close to that, this is pretty close to that, this is pretty close to that. Hey, not bad, right? And that's really what the third part of the Central Limit Theorem is saying, that the standard deviation for the sampling distribution is so regular that this is exactly the mathematical pattern. So even when you don't have an access to a simulation, you could just directly calculate the standard error of a sampling distribution of means just by using the third part of the Central Limit Theorem. Cool, right?